what I want to start with today, well, let me just recap where we were at the end of class last time. Last class, we derived the ideal gas law. And I just want to give a small perspective on the ideal gas law, which I think I kind of mentioned, but I want to reemphasize it. Right? It's this function P times V equals nRT. Other way we might write where this is moles, right? And this is 8.314 joules per mole per Kelvin. There's also a form of that is microscopic, where it's just a unit conversion, where n is the number of particles, and then you multiply it by kb. Right? So this is the number of particles. But there's no difference between the two of these. You're just, one is in, this has no moles in it, and this one has moles in it. Right? You use two different constants. Right, and I want to give a little thermodynamic perspective. Right, this is a class about thermodynamics, about heat, about the interpretation of this formula. Because when you learn this formula in general chemistry, you learn it without the context of what it means. Right, you just learn a simple formula that there's some empirical background. Maybe if you remember, I don't know if you remember this, but you talk about Dalton's laws and Boyle's law, pressures and stuff, and they're just versions of this law. You don't really understand the kind of fundamental physics of this equation, and it's very simple to understand. And the idea is that in an ideal gas, by assumption, all expressed energy, so any form of energy in this gas, is kinetic energy, right? It's just motion. Because the particles can't interact with themselves, so there's no potential energy forming. We'll talk a little bit about that today. And so a really interesting way to look at this is to think about it in terms of energy. So just as a reminder, if we do the unit analysis on this, the units on this are proportional to joules, and the units here are joules, right? Depending on what units we use for pressure and volume, but you're just equaling some type of energy to another type of energy. And all this is telling you, we have a kind of intuitive sense of what nRT means, right? This is the thermal energy available, right? You can think of it of a couple different ways. If your box is insulated by a heating material or cooling material, that thermal bath, right? If you put it in a jug of water, that water is providing the thermal energy to maintain the temperature of the gas. Or you can think, well, maybe I heat the gas up itself. All the energy is contained inside of it. It's not feeding in through the box from the bath. And it has some temperature involved to it. Right? So that's the right-hand side of this equation. And then what's the left-hand side of the equation? All this is the energy required for a gas to maintain a volume at a given pressure. In order for the gas to have enough energy to express a shape with some pressure and volume, it has to have some kinetic energy, right, to do that. So P times V is that energy. P times V is the energy that is required for the gas to fill the box, if you will. And so all ideal gas says is that, the ideal gas law says is that the energy required for this gas to maintain this is just all that's being used is the thermal energy, right? This is the source. Right, so this is like the source of energy, if you will. Depending on who you ask, they might say that this is the source of energy, but let's not worry about that right now. And this is the response. The left-hand side is the response. Temperature, if you will, the thermal conditions of your system provide the system with energy, and that's just enough energy to fill up the box. Right? Once these are equal, you're done. So for instance, if you had, this is a ridiculous idea, but imagine you had this very, very discrete, very, very clumped up gas, right? Very small, and you put it inside of a big box, like this. Right? You have this gas that's all compressed in here at some temperature, and you just let it expand so it fills the box. The energy required is PV to fill that box. Okay? Very simple. The only reason why this works is because we assume that the molecules don't, or the atoms don't interact with themselves, right? All they do is move around like dumb billiard balls. That there's no attraction, there's no repulsions. The only thing they can do is just float around, move randomly, and the amount of energy it does to take and fill a volume at a given pressure is P times V. And that has to be equal to nRT, because this is the only source of energy we have, the heat, the thermal energy, if you will. Okay. Any questions about that? Okay, so that's pretty straightforward. What we're going to do today is look at how this breaks down. And because we're going to have to start relaxing some of the conditions, because some of the ideal gas law conditions are obviously untrue. Molecules are attracted to each other. Molecules repel each other. When they collide, they exchange energy. They're inelastic collisions. So there's things that break down, and we have to account for those. But before I do that, I want to tell a story. Kind of an aside. The idea is there any question I want to ask, is there any physical imperative for molecules or atoms to be attracted to one another? Let me write that down. What's the word? I want to use impetus, but that's not really the right word. Yeah, let's say that. Is there any obligation for molecules or atoms or materials, any material, to be attracted to themselves or repulsed? Let's worry about repulsions later. Let's just think about attractions for a second. The answer is very interesting. I don't want to spoil the answer, but instead I'm going to come up with an experiment to test the answer. And it's actually an experiment that physicists have done, and the result is really beautiful. So, of course, we know that molecules are attracted to each other, right? For instance, let's look at the dimer of water, right? So water 2. Okay, so 2 waters hydrogen bonded together. It looks like this. Remember, oxygen has 2 lone pairs. Something like that. So what happens in a hydrogen bond? Right, this is not a covalent bond. Let's ignore that. Obviously, atoms are attracted to each other. They form bonds together, but that's slightly different than what we're talking about here. But here we have 2 molecules. There's no unpaired electrons. They're just normal molecules. And 2 water molecules, when they come together, they actually have quite a bit of an attraction. It's on the order of about 50 kilojoules per mole. The attraction energy, the hydrogen bond energy. And the reason why a hydrogen bond is so strong is an electrostatic. So a hydrogen bond is an electrostatic effect, which means that positive charges are attracted to negative charges. Like opposites attract. It's an electrostatic effect. And that can be easily rationalized by the fact that these lone pairs have a significant amount of negative charge on them. There's a dipole in the molecule that draws the electron density away from the hydrogens in this direction. And so you have all this negative charge on the oxygen atom, and you have a lot of positive charge on the hydrogen atoms. So when 2 waters get close together, you've got a negatively charged lone pair that kind of sits away from the oxygen atom, or they kind of sit far out. And you have a hydrogen that sits far away from its negatively charged oxygen. That's very polarized positive. So you have a negatively polarized lone pair and a positively polarized atom. Not surprisingly, they're attracted to each other. Okay, but that's pretty straightforward because we can always use charges, right? We can always use negative and positive. But now here's another question. What if we take 2 helium atoms? Now, if you remember, helium has a full shell, right? So they can't pair together, right? You can't form a dihelium. That's not a real molecule necessarily. But there's no, heliums are just balls, right? They're just balls of negative charge. And they're exactly identical. So as they come together, there really isn't any much difference between the two, right? There's no plus and minus going on, really. You just have two balls of electrons, and they don't really attract each other very much, right? So we would say, okay, well, there's probably no attraction between two helium atoms. But in fact, that's completely incorrect. In fact, okay, I don't want to spoil it, but I'm going to anyway. What you're going to find, and this is a really beautiful fact about chemistry, is that any electronic matter, any atom, any material, any molecule is inherently attracted to another one. Any sort of bound state of protons and electrons and neutrons that combine into a single particle, right, helium or water, is always going to be attracted to another one. So even though we say that helium doesn't form a bond, heliums are attracted to each other. It's a very, very small attraction, but they are attracted to each other. And that seems very counterintuitive, because everything we understand about bonding is this idea of polarization, right? Negative charge moving away from positive charge. But in fact, there are systems that you can identify experimentally that don't have this at all, formally, but are still attracted to each other. And for a long time, so this was understood in the early 1900s. There's a man named van der Waals. Maybe you've heard van der Waals attractions before. He's a Dutch chemist, van der Waals, who came up with a theory about these kinds of attractions between these species that would otherwise you wouldn't consider being attracted to each other. So he kind of understood this empirically, but he didn't really understand why it is. There wasn't really a microscopic theory for this. Like what is the fundamental reason why two heliums attract each other? And so this has been a question that was open for a long time, and it wasn't until the 1970s or so that physicists were able to really test this at a fundamental level. And the way they do this is a beautiful experiment. Again, the only reason why we know two heliums might be attracted to each other is empirically, because in the 1900s there's no way to calculate it, but empirically we had a sense that, for instance, two argons are attracted to each other, very similar. Physicists test it in a very simple way. What they do is they make an apparatus where they have two sheets of metal. Let's see if I can draw this. Okay, so you have a sheet of metal here. Let's just say aluminum, right? Piece of aluminum metal. It's not charged. There's no voltage running through it, so there's no electrons. It's just a normal piece of metal, free field. There's no electricity, nothing going on. Just a piece of metal. And what they do is they put it close to another piece of metal, which are all with red, and separate it by some distance. So you have two pieces edge on, face on like this. That's not a very good drawing of it, I'm sorry. But the idea is that you have two pieces of metal like this, right? Okay? And there's a distance separating them. We'll call it x, delta x, right? There's a distance between them. Okay, and then on the second piece of metal, they attach it to a spring. So here's my spring. And they attach it to a wall, right? They attach it to the wall, right? And so they set this spring so it has no tension. Right? So the weight of the metal attached to the spring is equal and opposite to the returning force of the spring, right? So they don't want to stretch it out so the spring wants to come back. They don't want to compress the spring so it wants to expand, like a slinky. So instead they set it perfectly at equilibrium. We call this at equilibrium. And what they do now is take this other piece of metal that's not attached to the spring and put it on a moving stage. A stage that can move closer and further. Right, you just have a little stage where your metal piece is attached to it, and you can bring it closer or farther away from the red aluminum plate. Okay? Now, we want to get them very close together. Okay, so maybe we want to get them within a couple microns of each other. Very, very close. Not touching, but very close. And what we're going to do is a function, we're going to plot delta x as a function, or versus, let's say this, plot versus x, versus the detected force on the spring. Okay? So the idea is that as this black metal piece starts to get closer to the red one, if there's a repulsion or an attraction, the spring's going to move. Right? If the pieces of metal are repelled from each other, so if the pieces are repelled, the spring is going to move backwards, right? The red material is going to move, the red plate's going to move away if it's repelled by the black one, or it's going to stretch if it's attracted. Right? Because it wants to draw that red one closer in. Okay? These two pieces of metal are the most boring pieces of metal you can possibly imagine. They're completely flat. There's no voltage running through them so that there's a charge buildup. Nothing. They're just plain neutral plates of metal. Now my question to you is, what happens to the spring as I bring the black plate closer to the red? There's three answers. One is that they repel, one is that they attract, and one is that they do absolutely nothing. What do you think it is? Take a few seconds to think about it. Imagine doing this yourself. Two boring pieces of metal, like maybe you cut two pieces of metal off your car, right? And you put them close together like this and have this experiment. What do you think is going to happen? Well, they do. That's right. They attract each other. Now, if we think normally, and I kind of spoiled that, right? Because I've said that the things are attracted to each other even when it doesn't seem like they are. And there's no reason to suspect that these two aluminum plates are attracted to each other. They're identical. There's no charge. There's no negative charge on one and positive charge on the other. Right? There's no voltage, no current, nothing. They're just neutral plates. But in fact, the answer is they attract each other. So once you get to a certain distance, you can actually measure that this plate stretches the spring a little bit and tries to get closer to the black plate. The plates are attracted to each other. You can actually measure this. Now there's a theory to prove it. There's like a theoretical model for this. And I'll tell you what the title is in just a second. But the plates are attracted to each other. This is what's called the Casimir effect. Now, we're not going to do anything more advanced about the Casimir effect because in order to understand how this works, you need a lot more physics. So we're not going to talk about that. But the important thing is the take-home point, is that no matter how boring the material is, how exactly same the two particles are, they naturally attract each other. And it doesn't matter. As long as there are electrons, electronic matter always attracts one another. So it doesn't matter if we have water, helium, hydrogen atoms, argon, you name it. There's always a natural attraction. And so, well, that leads us to a problem. Well, that means the ideal gas law is immediately invalid because, well, everything's attracted to itself, right? There's no such thing as two unattracted plates or two neutral plates. If things get close enough together, they're going to attract each other. Now, if they get too close, then they might repel each other, right? For instance, as we'll learn, if you plot the energy of attraction between two helium atoms as a function of the distance between the two atoms, what you find is that when they're really close, when they're overlapping, the energy is really high. And then as they start to fall apart, they go to negative energy, which means they're attracted, right? So zero energy means no attraction, positive energy means repulsion, and negative energy means attraction. And then at long distances, it kind of narrows off. But there's this region where two helium atoms are going to be attracted to each other. Now, once they come close together, if you think of them as spheres, eventually they're going to be, one sphere is going to be overlapping the other one, and that's where they start to press apart. Right? That's repulsion. But there's always a balance between repulsion and attraction in molecules and atoms. And so we would expect it in our ideal gas. Right? If the average distance between, so let me write this down more explicitly. Let me not use purple. The idea is that at a long distance, right, imagine this is the average distance in our box between two atoms in it. So at long average distance would be low pressure. There are no forces, repulsive or attractive, right? Everything's so far apart that they barely see each other, right? So in an ideal gas, if it's at low pressure, that's fine. If things are really, really close together, short average distance, strong repulsive forces. So at high pressures, right, where we're going to see a short average distance, we're going to see deviations from the ideal gas because these molecules, these atoms, and these particles have some repulsive forces, right? That's going to want to push them apart, right? So we expect a breakdown of the ideal gas law there. Likewise, at intermediate distance, intermediate average distance, you either have weak or strong attractive forces. Generally weak, right? But they're attractive. How strong or how weak they are, it depends on the molecule, right? But every molecule and every atom universally shows this behavior. Right? How attractive they are, how fast they repel, how close do they have to be attractive, right? What distance is this minimum energy? All depend on the material. But every single molecule, every single atom will show this behavior. It's universal. Okay, so what that tells us is that there's a region where the ideal gas law works really well. And that's only at long average distances. All right, so the assumption of the ideal gas, all gases reach ideality when the distance between each particle inside the gas is at basically infinity, right? So infinite volume or zero pressure, however you want to think about it, either way, it's fine, is where the ideal gas law works. But the interesting thing is that as you start to approach shorter and shorter distances, you start to get forces. You start to get things that aren't just kinetic energy affecting your energy balance, but they change. And there's a scale at which they change from attractive, which always comes first. So as you start to get closer and closer, they become attracted, and then once they get too close, they repel. Right? And every molecule, every atom exhibits this behavior. Now, in my notes, I haven't posted them yet. Maybe it's on a different page. Oh no, here it is. There's a model for describing this theory, and in fact, on the problem set, there's a question about it. And I'd like to talk a little bit about it first before we dive into the gas laws, because it's nice to think about a little bit of kind of fundamental chemistry here. So there's a very simple model that chemists have used for a long time to model these weak interactions, right? Things that you can model for hydrogen or for helium or carbon dioxide. Two carbon dioxide molecules don't really have a strong attraction to each other, but they do attract. And the model that we use to measure this, or the model we use to describe this behavior, is what's called, let me just delete this. It's called the Lennard-Jones model. And most materials, most neutral materials, molecules and atoms that have paired electrons, right, that aren't positively charged and negatively charged, right, absence of these charges, right, tend to follow these Lennard-Jones like potentials. And what do I mean by a potential? A potential is a function of position versus a function of position that returns energy, potential energy. So what you can think about is that potential energy is again made of the same stuff as kinetic energy, but it's represented a different way. Kinetic energy is just the force of motion. Potential energy is some energy that is stored inside of a system that can be used for other things, right? Let's use this example right here of these helium atoms. Right? At long distance, it's all kinetic energy, right? Because there's no forces attracting the two helium atoms to each other, repelling them. But let's say we're in a situation where the average distance between the two heliums is in this region where the energy is negative. Well, then there's this extra bit of energy that each pair of helium atoms stores, right? This is that attraction energy. And in order for the system to remove that energy, you have to pull the helium atoms apart. And you have to pull them apart by this much. Does that make sense to everybody? Right, we're going to see this time and time again. Right? You can describe bonds this way too. Bonds look a lot like this. And the idea is that a bond, right, like say this OH bond, stores some potential energy in it, because that's the energy it takes to break it apart. Right? So you can always use that energy for later. You can think of potential energy as stored energy, energy that has the potential of use at a later point. Right, so bonds have a lot of potential energy, and helium atoms between each other have a very small amount of potential energy, but it's non-zero. And so the Lennard-Jones potential, right, is going to be a function V. We often write V for potential energy. I'll write that here. Often I'll write kinetic energy as T. This is just convention. And V is potential energy. I have no idea why they are this. They just are. Must be a different language. So when you see V, you can often think big V, you can think of potential energy. So I have a function V. That's a function of the distance. Or R is the distance between the two helium atoms, or any sort of species. And it has a very simple formula that I'll try to describe to you. First, there's a constant on the outside called epsilon. It's times 4 for a specific reason. And it's a function of r to the minus 12 minus r to the 6 minus 6 power. Okay, and so there's these constants. I'll describe what the constants are. There's two constants, epsilon and sigma. I'll write this in black. Epsilon is called the well depth. I'll explain what that means in a second. And it has units of energy. And sigma is called, I don't know what they call it exactly. We'll call it the size, or the scale, the length scale of the interaction. And it's in units of length. If we look at this function a little more carefully, if we kind of just zoom, blur our eyes a little bit, this kind of looks like r to the minus 12 minus r to the minus 6. Which is kind of strange. But these 12 and these 6 actually have physical meaning. So, and I'll explain what they are. So the r to the minus 6 term is the attractive term. All right, so attractions go as r to the 6. All right, and the r to the minus 12 is the repulsive term. So if you think about what this function looks like as a function of r, if you're a very small r, where they're really close together, this term is much larger than this term. But as you start to get further and further away from 0, or as you extend the distances, this term, r to the 12th, gets very small, and eventually r to the 6th wins out. And so that's the idea that we have here. If you're really close, you have this very high asymptote from repulsion, right? It grows very quickly, like r to the 12th. And as you start to get further away, it disappears, and the r to the 6th term starts to win. That's the attraction term. So attractions kind of fall off more slowly than repulsions, but it's not as intense of a parameter, right? It's a factor of r to the 6th difference. All right, and as numbers 6 and 12 have good meaning, you can come up with a theory that explains that the attraction between, say, 2 helium atoms goes as r to the 6th. That's actually something you can prove. All right, so this is just kind of a general kind of empirical model for these things. And I'll draw it for you, and we'll explain what the parameters mean. So again, this is a function of potential energy, say in joules, versus radius, let's just say in angstroms, right? 10 to the minus 10 meters. An angstrom is a good atomic unit of length. The average distance between, the reason why we use angstroms is because and I'll show you, this is the reason why we use angstroms for atomic distances. Angstroms. For atomic distances is because the average distance between an electron and a proton in a hydrogen atom is on the order of 1.5 angstroms. Right, so you can say that the chemical length scale, if you will, is on the order of an angstrom. Right, bonds usually are, a carbon-carbon bond is about 1.5 angstroms, 2 angstroms, give or take. Right, this is just a good scale for us to use. Just as a reminder, this is 10 to the minus 10 meters. It's 100 picometers. So I'll use angstroms a lot when we talk about atoms and molecules because it's just a really good scale to use. Because most distances in chemistry tend to be on the order of 1 to 10 angstroms. Okay, let me change my graph just a little bit. I just want to change I want to put it in the middle instead. It doesn't matter. You don't have to replace that. You can just draw it the way. It just makes things easier. Okay, so let's see what happens. So when the atoms, just like here, we can just reproduce this graph effectively. When the atoms are really, really close together, they're highly repelling, right? They repel as a function of r to the 12th. So let me let me use blue for this. So right, you have this very steep function at low distance. That's the repulsion part. And then once you start to get further away, that repulsion part gets tiny, and the r to the minus 6 starts to win out. And what happens is now you start to go into negative energies. There reaches a minimum, and then it recovers back to 0, like that. This is not a particularly good drawing. Let me finish. Let me make this continuous. Close enough. Okay, so it looks like that. And it should make sense. The atoms are really close. The potential energy is positive. So this is positive energy, just to remind you. If V of R is greater than 0 of repulsion, and if V of R in this case is less than 0, attraction between the two species. Right, so what we're doing again, R is just the distance between the two species, 2 helium atoms, for instance. And so now the question is what, where these constants come in, And that's actually really simple. The well depth, how much attraction there is, attractive potential energy in the well, is minus epsilon. Okay. So the more attraction there is between two atoms or two molecules, the bigger its epsilon is. And then sigma gives you a sense of where the minimum distance is, where the distance where the minimum energy occurs. And of course, so the V min, the minimum energy occurs at, it turns out 2 to the 6th root of 2 times sigma. Right? There's a problem on the homework that makes you derive these quantities.
Does that say 1 over 6?
Yeah, 2 to the 1, 2, it's the 6th root of 2. So that's equal to, if this is better, sigma, 6th root of 2. And the reason why the 6 comes in is because there's a 6 here. Right? There's on the last problem, on the problem set, you derived this number. There's 2 to the 1/6 times sigma. There's a problem on that. Okay, so this is a really, really nice model because it explains everything that we want, right? It explains repulsion at close distances. It explains attractions at intermediate distances, and it explains that nothing happens at infinite distance, right? It goes to 0. And just as some examples, hopefully I have them here. Yeah, I do. I'll just give you some examples of what these numbers look like for different species. So for instance, helium, I'm going to give the epsilons in Kelvin, which is a little confusing, but you can, again, temperature and energy are interconvertible by using Boltzmann's constant or the gas constant, so it's proportional energy. Helium has an epsilon equals 10.22 Kelvin, and its sigma is 2.56 angstroms. All right, so that's how much attractive energy two heliums have at this distance, roughly. Well, it's 2 to 1/6 times this. But let's look at a molecule that may be more interesting, something like oxygen. Oxygen has an epsilon of 118 Kelvin, right? It has just 10 times the attractive strength of helium, but has a longer distance. 3.58 angstroms. Do I have that right? Picometers is 12. Yeah, that's right. So it's interesting, right? You would expect that, maybe you would think, this might be a reasonable intuition, is that the stronger an attraction is, the closer two things want to be together. But in fact, what we see here is we have an attraction that's 10 times stronger than helium to itself. I'll just remind you that this is the attraction between two helium atoms, and this is the attraction between two oxygen atoms. It's 118, right? It's 10 times stronger. Right? The well depth, the amount of potential energy that interaction stores is 10 times more, but it's at a further distance. But the reason why it's at a further distance is because oxygen molecules are a bigger molecule, right? They have more extension, right? So they have to be further apart because they're the lone pairs, right? The lone pairs extend very far out away from the oxygen, and so that wants to keep them a little further apart, right? Because you don't want the last thing you want are two electrons touching each other. So electrons are attracted to each other up to a certain point, and then they really don't want to be near each other. So with oxygen, you have these lone pairs that are really far out of the molecule, and so that tends to keep things further away. All right, so this is just an example. These are really, really small energies. All right, so I'm just going to do a quick conversion for you because I can't remember it off the top of my head. I'm going to convert that into kilojoules per mole because I don't remember the conversion off the top of my head. What's the first one? 10.2? Right. This energy is 0.084 kilojoules per mole. Does anyone know what the average carbon-carbon bond length or bond strength is off the top of their head? The amount of energy it takes to break two carbon bond, a carbon-carbon single bond? Any idea? It's about 400 kilojoules per mole. Right, so this is an extraordinarily weak interaction, right, compared to a chemical bond. All right, it's like, let's see, that's 1, 2, 3, 4 orders of magnitude, factor of 10,000 weaker. Okay, and so you can imagine this is about 10 times more, so this is about 0.84 kilojoules per mole. Very weak, but it's real. It's real, it's measurable. Someone has actually detected helium dimer before. It's a real thing. It does exist, and actually the experiment to detect that's very elegant. They do the dumbest thing possible to detect it. It's really cool experiment. But yeah, so anyway, any molecule, any atom has this kind of attraction. You can see they're pretty small, right? On the order of much smaller than a chemical bond. So what does that tell us about the ideal gas law? Well, it says that the ideal gas law isn't going to work always. But the corrections to the ideal gas law are pretty small because the potential energy stored in these attractions are pretty small. Right? So the deviations are going to be quite small from the ideal gas. Questions about this? Okay. How much time do we have left? 15 minutes. Great. So I'm not quite getting through this as fast as I wanted to, but that's okay. I think this is an interesting topic. Hopefully, if you're here next semester, if we have time next semester, I'll go through the physical theory of why this happens in general. Right? Even though there are different ways to prove that all molecules and all atoms have attractions to each other, there's different ways to do it, and there's a way that's really amenable with quantum mechanics that you learn at the undergraduate level. We can talk about that next semester. We don't have quantum mechanics yet, so it's kind of hard to talk about. In fact, at this point in math, or in this part in chemistry, when we're talking about these things, quantum mechanics haven't existed yet, so we're not quite there yet. Okay, so the idea is now we can use this model to talk about how atoms in a gas are attracted to each other and how this might affect, you can imagine that this might affect our energy balance, right? Because we assume that the only energy inside of our box of gas was kinetic energy, but in fact there's a little bit of potential energy as well because of the attractions or the repulsions. All right, so let's look at that now. Let's go to our box of gas and look at that. Actually, I have a plot for you today. I'm going to go ahead and erase all this. So the thing is how are we going to test when the ideal gas law breaks down? And there's a really easy way to do it. Let's look again at the equation for the ideal gas law. PV equals nRT. All right, I'm going to make some adjustments to this equation to make it simpler. I'm going to divide both sides by n and write V over n as V bar, which is what's called the molar volume. Right, which has units of liters or whatever you like for your unit of volume per mole. Right, so this is at a given temperature and pressure, how much volume does a mole of your species, of your particles or whatever, occupy? Right, this is the amount of volume 1 mole of a gas occupies. At a given temperature. Okay, we'll use this all the time. Right? It's really convenient. Because remember, volume is a size extensive property, but when we divide it by the moles, which is also extensive, we get an intensive property. Right? This is fixed for a given gas at a given temperature. Okay, so this is an intensive variable. Right? So it's a useful one. because we can use it to compare different gases, independent of what volume our box is at. Okay? So what we can do now is rewrite PV equals nRT as, oh, well, that one's dead. P times V bar equals RT. Now the nice thing about the ideal gas law is we can divide both sides by RT. And we get P times V over RT equals 1 for an ideal gas law. All right, so we can go into the lab, make a box of gas, measure P, measure V, measure T, and then take the ratio and see what happens, right? If it's a perfect ideal gas, we'll get 1. Now, as a fun question, I'll let you guys do this calculation. This is a really simple question. What is, for an ideal gas, what is the volume of a gas at 1 atmosphere and room temperature? How would we calculate this? Any ideas? How do we tackle this problem? Well, let's see. We got pressure equals, we got how many moles do we have? Oh, sorry. What is the volume of 1 mole of gas at 1 atmosphere, 298.15 Kelvin? Sorry, 1 mole of gas. All right, so we know a couple things. We know N is 1 mole. We know T is 298.15 Kelvin. And pressure is 1 atmosphere. Okay. We're looking for V. Well, we have an equation for that, right? All right, we can just take Pivner. We're solving for V, so we divide both sides by P. Okay. So let's plug things in. 1.00 mole. We don't know the gas constant for atmospheres yet, but we'll come back to that. Times 298.15 Kelvin. And I'll divide by 1 atmosphere. Okay, so we don't know R yet. Because we're in units, right? We have atmospheres here. It's not in normal SI units, so we need to convert. So the units of R, though, we know, because we need to multiply moles in Kelvin and divide by atmospheres and get volume out. Right, so we know that there's going to be a liter in the numerator, right, because we get liters out. We have atmospheres. We divide by atmospheres, so we need atmospheres in the numerator. And we need to get rid of moles in Kelvin. So we need the gas constant in liter atmosphere Kelvin mole, per Kelvin mole. Okay, and so you can convert it, or we can just look it up. Literally, if you type gas constant on Wikipedia, Wikipedia has the value of the gas constant for every unit you would ever want. And so I'll just write it here. R is 0.082. Always forget the rest of the numbers. 057366. Now, that's in liters, atmospheres, Kelvin, mole. Okay. So, again, we don't need to use all these numbers because let's look at our significant digits. We have 3, 3, and 5. So we probably only need 5 digits here. All right, so that's going to be 0.0, 1, 2, 3, 4, 5. So up to the 7, 82057. Okay. I want someone calculate this for me, if you don't mind. So I'm a big Wikipedia fan. I will always suggest Wikipedia for things. Wikipedia gas constant. If you forget the gas constant and need it, just Wikipedia, and there's a list of them on the main page. It's a good resource. People who say you shouldn't use Wikipedia are haters. 24.5. Oh, I know my problem. I'm sorry. So let's change that back. That's not the number I want. So standard temperature and pressure is 273.15. Sorry. So let's change that. That number's a little large. So that's 0 Celsius.
22.4.
Yep. All right, we have 4 significant digits. Meters. No matter what ideal gas you have, doesn't matter if it's benzene, helium, hydrogen, uranium. It doesn't matter. If it's an ideal gas, it will always fill this volume, 1 mole. It's independent of the material. Right? What we're going to find is what's dependent on the material is the deviation, right? Because it's not nothing's a real ideal gas. So some materials might deviate a lot from this number, and some won't. And so let's look at that. All right, so we know no matter what, if we can measure our temperature, we fill our tank up to 1 atmosphere, we always know it's going to fill 22.4 liters. And if it deviates from that, we know there's something up. It's not an ideal gas. And that deviation is important. What we're going to do now is go into the lab and do this measurement. And we're going to do it as a function of pressure. Right? We're going to measure, let's see. Yeah, we're going to measure this ratio as a function of pressure. Okay? Now, it's the same thing as measuring the volume as a function of pressure, but let's just do it because we know the perfect answer is 1, and that's a really nice number, right? If we know it's close to 1, then we're ideal, right? As opposed to measuring whether we're off by 22.4 or not. And you find some really, really interesting results. So I'm going to draw a graph here. This is pressure in bar, or atmosphere, however you'd like to think of it. And on this axis, I'm going to measure the ratio PV over RT. Right. We know that the ideal result is going to be 1. And let me plot a couple more here. Thanks. And we'll make this 0.5. Okay. So I'm going to draw a line across 1.0. That's our ideal gas limit. And we're going to measure this ratio for different gases as a function of pressure. And we're going to do some big pressures. We're going to run up to 1,000 bar, 1,000 times atmospheric pressure, which is a lot. Okay, if it were an ideal gas, a perfect ideal gas, no matter what pressure we have, we're always going to have 1, right? So there's our ideal gas. Right? It's not going to change, even though my drawing makes it look like it's changing because I can't draw a straight line. But I promise you it doesn't change. So now what we're going to do is we're going to stick helium in our apparatus. And what you find with helium, let me see where this goes, like 1.4. So it's like right here. Is that it slowly increases as you increase the pressure. Oh, that's close enough. So what does that mean? That means that as pressure increases, this ratio is increasing. Temperature is being held constant, right? We're holding the temperature constant, so T is never changing. The only thing that can change is V, or V bar, rather than molar volume. So what's happening as pressure is increasing is that the molar volume is increasing. Right? So because P is increasing, if it were an ideal gas, nothing would change with this ratio. But the molar volume increases of increasing pressure for helium. What does that tell us about helium? That the higher the pressure, the more volume it takes up per mole. What does that tell you about helium at high pressures? Yeah, what's that coming from, though? You're right, though. Right? There's some new energy appearing in here that's causing a deviation, right? But is that an attractive or a repulsive energy? I'm sorry, say it again? Repulsive, exactly. Because it takes more volume than you would expect for this helium to exhibit this pressure. Right? The heliums are pressing each other out. Right? That's exactly what you expect. And most gases work this way. It turns out that the more complicated the molecule becomes, the behavior becomes strange. Maybe not strange, but different. So for nitrogen, right? Nitrogen is a diatomic, right? It's not an atom, but a diatomic. It grows more slow. Let me not use red because that's red. We'll use blue. Nitrogen starts out low and then slowly increases to the point where it's above nitrogen or above helium. Okay. Now the reason why nitrogen grows more slowly is somewhat of a complicated, there's a somewhat complicated reason, but it's the fact that when two nitrogens come together, sorry, here's nitrogen, right? And another nitrogen comes in, and they come in end on end, like this. They can also come this way too, but we'll look at this way. As this ball of electrons starts to approach here, nitrogen has an ability to kind of move its electrons away. Right? So you've got this ball of electrons coming in, and so what's going to happen is that the electrons are kind of going to shift in this direction, and you get a positive charge and a negative charge here, right? So that allows these electrons here, right? This is just a ball of electrons, if you will, and nuclei. And the molecule that accepts it kind of shifts its electrons away from that end in order to facilitate the molecule moving in. Right? So nitrogen kind of has an extra degree of freedom. Helium is just a sphere. It can't do anything, really. But nitrogen can move electrons along its bond to polarize it a little bit. Right? So we call this induction. Right? It's an induced effect polarization, an induced electrostatic effect being induced by an incoming molecule. Right? And so what that does is that as the density of them get close, as the pressure increases, as the density of nitrogen atoms or nitrogen molecules increases, it moves more slowly up because it can shift electrons around on a microscopic basis to get things oriented right. So it grows more slowly, but eventually you hit a critical point where all these nitrogens are so close together that you can't compensate for that, and it just blows up. Right? So nitrogen is a little complex because of that. And so oddly enough, that at reasonable pressures, despite the fact that nitrogen is a more complicated molecule, it's actually more of an ideal gas than helium. At intermediate pressures, rather. Kind of, 100 bar. 1,000 bar is crazy. Like that's a lot of pressure. So we're talking really high pressure here. Right? It's hard to describe how much pressure 1,000 times the atmospheric pressure is, right? If you weigh 100 pounds and you're at 1,000 bar, your body feels like it weighs 100 times 1,000, whatever that is, 100,000 pounds. Okay? That's a lot of pressure. So very high pressures. But that's the idea, that the nitrogen can kind of shift electrons around until it can't anymore, and then you just have balls of electrons bouncing off each other and it explodes. I'm almost done here. So I just wanted to show one more, and that's methane. Now methane is a really boring molecule. Okay, organic chemists are going to kill me for saying that. But it has no dipole moment, right? It's a neutral molecule, methane. It has very weak attractions to itself, but it has an interesting geometry, right? It's tetrahedral. And it turns out that tetrahedral geometry, and the fact that it's got 4 different carbons, that it can break that tetrahedral symmetry with the electrons and kind of orient itself. You can kind of think of it kind of looking like this, like an sp3 carbon, where one of the hydrogens is electrically polarized and the other ones are negatively polarized. Right? And they can do that across all of them. Right? So you can kind of distort methane quite a bit when it gets close to itself. And interestingly, when methane does that, in intermediate pressures, there is a negative deviation that eventually, as it gets closer and closer, increases like that. All right. So what are we saying about the methane molecules when there's a negative deviation like this? What does that imply about them? They're attracted to each other. Exactly. Right. And the reason why is because of the fact that CH4 has all of these different hydrogens and it can distort itself. These are very, very small contributions because these are very weak interactions. So this is kind of a really like sophomoric way of looking at it. But the idea is sound, that there's more ways for the molecule to distribute its electrons to get everything fit in nicely. And it's just enough that it can actually deviate negatively. Right? This is where methane likes itself. But eventually, once you hit the high pressures, it does like everything else, right? You hit the repulsive tail, and everything wants to blow apart, right? But there is a region in methane where this is negative. You can imagine water, for instance. Water has very strong attractions. Water has a massive negative deviation. Water looks like this. Well, water's tough because water might look like this. And then eventually it flattens out because once you compress water enough, it becomes a solid. So that's a little tricky. This is H2O. But water has a huge deviation because water molecules are naturally very attracted to themselves. So water is a very, very poor ideal gas. Okay. All right, so I'm done for today. I'm over time. So on Thursday we'll come back to this and we'll talk about some corrections to the ideal gas law that will allow us to talk more about these deviations and be able to predict them. Okay, have a lovely day, everybody. And we'll do some calculations.